According to CIO research for 2025, 88% of AI agent projects fail before they ever reach production. That gap exists because the flawless illusion of a local Jupyter Notebook demo does not survive the chaotic, fragile reality of an enterprise production environment. For our developers here in Pakistan, we need to get specific about what we are actually building. Wrapping an OpenAI API call inside a standard Python script does not make an AI agent. That is a glorified workflow. It is advanced Jugaad, executing a rigid sequence where the language model is just another tool sitting on the assembly line. True AI agents represent a shift in the locus of control. Decision-making authority moves away from human-written code and transfers directly to the language model at runtime. To see exactly how that works, we are going to deconstruct the code-level difference between these systems, analyze why autonomous agents fail so disastrously in the wild, and explore how enterprise teams use multi-agent architectures to survive. Misunderstanding this structural shift in control is exactly why startups burn through their cloud budgets on broken deployments. Architectural clarity is a matter of survival. We establish our baseline with traditional automation, the deterministic pipeline. Human code dictates every step. Data is extracted, classified, summarized, and notified. Even if an LLM is doing the classification, the data moves past it down the exact same linear route. The path is hard-coded. Building these rigid manual processes requires a lot of upfront requirement, anticipating every possible input. The middle ground is the orchestrated workflow. Here, the LLM acts as a route. It reads the incoming data and picks from a predefined dictionary of functions, directing a query to the billing department or technical support based on the text. The LLM chooses the branch, but a human developer still built and constrained all the available tracks. It cannot invent a route that does not exist in the code. That brings us to the autonomous agent. This operates on a react loop, reason and act. The language model entirely owns the control flow. The agent receives a goal, selects a tool from its environment, observes the output, and decides its next step dynamically based on that fresh context. If you're managing dynamic supply chain logistics for a local delivery service, an agent can check traffic APIs, detect a blocked route, query a secondary database for alternative drivers, and dispatch them, all without a predefined script telling it what to do next. This open sandbox allows the system to process unpredictable, unstructured data that would break a fixed script. But it also removes the safety rails of traditional code, exposing the entire system to catastrophic errors. Traditional software fails cleanly. You get a 500 server error, you check the logs, you fix the bug. AI agents fail differently. They suffer from silent quality degradation. An agent will complete a task, return a confident output, and never throw an error code, even if the underlying logic is entirely corrupted. Tracking down these silent issues creates a massive roadblock for engineering teams, because the system insists everything is fine. The most dangerous proximate cause of this failure is tool misuse. Give a data cleanup agent overly broad file system access, and it might decide your production folder is redundant and delete it entirely without asking for permission. This leads directly into context drift and hallucination cascades. If an agent makes a minor reasoning error at step 2 of a task, it silently propagates that mistake. Because the outputs remain syntactically valid, it corrupts the next 18 steps of the workflow before anyone notices. Writing code that puts the agent in an infinite retry loop does not solve probabilistic errors. It just ensures the model drains your cloud API budget in 3 minutes trying to solve an impossible prompt. Treating a probabilistic reasoning loop like a deterministic script is the root cause of that 88% failure rate. You cannot fix structural fragility with better prompting. When developers try to scale, they often assume more agents mean more intelligence. Throwing 10 autonomous agents at a complex problem just creates chaos. Without a designated architecture, systems suffer from bureaucratic bloat and consensus hallucinations, where agents talk in circles and reinforce each other's errors. To solve this, enterprises rely on the supervisor pattern. A master conductor agent plans the workflow. It delegates narrow tasks to specific worker agents and strictly verifies the return data before moving to the next step. This pattern is highly effective for strict business tasks, like fintech loan approvals or customer onboarding, where exact sequence and strict oversight are mandatory. The alternative is the swarm pattern. Swarms operate as autonomous peers. There is no central boss. They are highly scalable and excel at open-ended exploration, like massive web scraping operations, where agents pursue independent leads. However, swarms are an absolute nightmare to debug. There is no central audit trail, making it incredibly difficult to track agent handoffs when things go wrong. Architecture dictates your performance ceiling. Picking a swarm for a highly sequential workflow guarantees a failed deployment. The 12% of companies that actually reach production share one trait. They invest heavily in resilience engineering long before they deploy. The core component of that resilience is the AI agent circuit breaker. The circuit breaker monitors failure rates. When it operates normally, the state is closed, allowing autonomous execution. If error thresholds are breached, the circuit trips to open, freezing the agent and escalating the task to a human operator. Before the agent returns to full autonomy, it enters a half-open state, forcing it into a recovery testing mode, where selective tasks run with full validation. Traditional automation is not obsolete. For high-volume processes with structured rules, it remains the most reliable and cost-effective solution available. If a simple if-else statement solves 80% of a workflow, do not overbuild an agent. Keep agents exclusively at the edges of your systems, assigned to unstructured data and complex reasoning tasks. For engineers looking to scale, the focus must move past the happy path demo. Reliability is an architectural problem, solved by building robust, fail-safe systems that survive the reality of production.